we finished up last time with this thing called the fundamental theorem of calculus. Fundamental theorem of calculus 2, actually. Fundamental theorem of calculus 2, which said that that if you're looking for the integral of some function, if you're looking for the definite integral of some function, then what do? Dana, what do?
If that would, you take the antiderivative of that, and then you plug in, so it'd be like big F. Big F would be minus big F.
Right. So the setting is like this. The conditions are like this. You have some function that's continuous on an interval. Okay. So this is important. It has to be a continuous function. So you can't play this game if the function's not continuous. And if you have f a antiderivative of little f. So as long as you have a continuous function and you can find some antiderivative of it, then you can calculate the area under the graph by taking the difference of the function at the endpoints. Later on, when you take calculus 3, you'll see sort of cooler versions of this. One of which is like this. It's possible to. So this is sort of a funny statement, right? Because it says that you have some function, but in order to find the area, all you need to do is evaluate this other function at the endpoints, right? This other function at the endpoints. Okay. In Calc 3, you'll see things that are sort of like this. You're interested in. Suppose you're interested in the area of some object. Then it's possible to calculate something that goes over that just goes on this line here, and by looking at the line, you can get the area of the thing that it contains. Okay. They actually made a device called a planimeter, which will do this for you. So it was in the late 19th century, and they made this object so that you can, if you have some sort of strange object like this, you can run the planimeter over the path, and it'll tell you the area of the thing enclosed. Okay. So and that's based on something called Green's theorem, which is sort of a super version of the fundamental theorem of calculus. Okay. But you'll see several versions of the fundamental theorem of calculus in calculus 3. Okay. So so this gives you a really great shortcut, right? Somebody says, "I'd like you to find the area. I'd like you to find the area under this thing," and you say, "Well, all I need to do is find the antiderivative and take the difference of the antiderivative at the endpoints." Okay, right? But that's of course not the way that you define the area, right? The way you define the area is with Riemann sums, approximating it, and then letting the Riemann sums become infinitely fine, right? Right? If you went to a child and you said, "What's the area? What is area?" and you said, "Well, you need to take the antiderivative and evaluate it at the endpoints," right? That's not at all how one thinks of area, right? That's not the definition of area. Okay. So do we have time to talk about why this happens? I hope so. Let's try. Okay. So why do we believe? Why does this happen? Why is this true? Right? Why is this true? Why is this true? Right? Okay. Here's one explanation, and we'll give another explanation in a couple days. Here's the idea. So you have your function f, right? You have your function f, and you have, right, big F is the antiderivative. Okay. Now, let's chop this thing up into a bunch of pieces. So partition the base. So let's partition AB into x0, x1, xn, where this is A and this is B. So partition the base, just as usual. Okay. And then, let's think about the mean value theorem for F, for capital F. Okay, let's think about the mean value theorem for capital F on each subinterval. Okay. Take a few seconds and write down what the mean value theorem tells you about capital F on each subinterval, you know, x0, x1, x1, x2, x1, x2, and so on and so forth. Okay. What does the mean value theorem say? Just write down something. Okay, somebody tell me, what does the mean value theorem say? Luke?
Sorry, I was just trying to write that down.
Okay. Noor, how about you? What does the mean value theorem say? Mean value theorem.
There's a point where it's 0.
No, that's Rolle's theorem, the precursor to mean value theorem. There's a point where the slope is not 0, but
No.
nope. Nope. Amanda?
There's a point where the slope is equal to the slope of the tangent line.
Okay, slope of the tangent line, right? So there's a point. There's this point C in xi, let's say xi plus 1. So for each interval, right, each interval is going to look like something like this, xi plus 1. Right? There's a point where f prime c equals f of xi plus 1 minus f of xi over xi plus 1 minus xi. Right? That's the mean value theorem, right? Can anyone say anything about, does anyone want to say anything about this? F prime, capital F prime C.
It's not just lowercase f.
That's lowercase f, right? That's lowercase f. Okay, so in each interval, right, in each interval this happens. Actually, let me call these guys C sub I, because there's one for each I, one for each interval, C sub I, C sub I. Okay, everyone all right? We just, so for x naught, x1, right, there's this guy, there's this C naught where f of C naught equals fxi plus 1 minus, fx1 minus fx naught over x1 minus x naught, right? For the next guy, there's f of c1, where f of x2 minus f of x1, where you get f of c1 equals this quotient, and so on and so forth, right? Down to the last, the n minus 1 guy. F of xn minus f of xn minus 1 over xn minus xn minus 1. Right. So I've just written the same thing expanded, right? I've just written this thing, but just spread it out. Everyone all right? Any questions?
What's
Yeah,
the,
look.
what's the buff? It's xi plus 1 minus xi?
Yes, xi plus 1 minus x of I. Any other questions? Okay, so at this point, I'm going to multiply both sides by this denominator. Okay, so multiply everything by the denominator here, right? Okay, I'm going to get fx1 minus fx0 equals blah, fx2 minus fx1 equals blah, and so on and so forth. Okay, right, you can do that. That's legal. So I get fx1 minus fx0 equals f of c0 times x1 minus x0. fx2 minus fx1 equals f of c1, f2 minus x1, all the way down to fxn minus fxn minus 1 equals f of c n minus 1 times xn minus xn minus 1. And let me throw in something here, that these guys are evenly spaced, so that my partition, all the intervals are the same width. Okay. Okay, now you get to see something magical happen, which is add everything together. Add everything together. What do I get on the left-hand side? Oh, actually, before I do that, let me just call these guys delta x. These guys, I'm going to call all of them delta x, right? Because they're all the same. They're all the same width, right? Delta x is b minus a over n. So this part, maybe you see how things are going to all come together. On the left-hand side, something pleasant happens. Yeah, Win.
Well, fx1 is going to cancel out with fx1 in the next one, so it's just going to be fx0 minus fxn minus 1 in the end, if you add them up, right?
These guys are going to all cancel.
Oh,
So who's left over
those two.
are these guys, right? So you get fx minus fx0, remember x0 is a, and plus fxn, remember xn is b. Right. x0 was a, xn was b. So none of those guys in the middle mattered, but they all vanished. Now on the right-hand side, what you get is the sum of f c I delta x from I equals 0 to n minus 1. Okay. What's that? What is that? That's a what?
Isn't that the definition of the integral?
It's not quite the definition of the integral. This is a Riemann sum.
Oh, right.
But how would we get to the integral from here?
By plugging, by evaluating it on the interval.
Not quite. You've got these Riemann sums.
Oh,
Yep.
taking the limit.
Taking the
To-
limit, right. So then, right, so this thing here is a Riemann sum. Right, this is a Riemann sum, which in the limit yields the integral from a to b of f. So just take the limit. So take the limit. We get f of b minus f of a equals the integral from a to b of f. Evan.
Where did we get f of b minus f of a?
That was x naught is a, xn was b.
Okay.
So that's one way of seeing why the fundamental theorem of calculus is true, and you see that it's you can explain it using the mean value theorem.
Wait, how does everything else cancel out?
You've got fx1 minus fx naught, fx2 minus fx1, so the minus fx1 and the plus fx1 cancel,
Okay.
right? Got fx2, this is the minus fx2, those guys cancel, and so on and so forth. All these guys cancel, who's left over? This one and this one.
Okay.
Okay. So any questions about that? So this is one way of explaining how the fundamental theorem of calculus works. If you don't like it, don't worry. There's another. We'll see another way in a day in the next class. And I personally like the other way better than this way. Maybe you did. Any questions? No, you look like you want to ask a question. Do you want to ask a question? No. Okay. Okay. So let's go on. Okay, so basically last time, the main thing that we got out of it, was how to define the integral, right? So this class is about basic properties of integrals. Right. Last time we showed you have some function, you construct the definite integral as the limit of these Riemann sums. Okay. And so here's some simple properties. So first, some simple ones. One, the integral. Suppose you take the integral from a to a. Okay, so you have some function, and you take the integral, but it goes from not from a to some other point, but from a to that point itself. Okay. Well, then what's the integral going to be? 0, right? Why? Well, because when you take your Riemann sums, all the width of the interval is going to be like 0, right? You're going to take a height. Certainly, there's a height here. Right? You have some f of a, but it'll be times the width, but the width is 0, right? So the integral is 0. Number 2, the integral from a to b of 1 is what? Write it down, maybe. Take a second. Write down what the integral is. Okay, what is it? Kayla?
Is it b minus a?
B minus a, right? b minus a. You can see it in two ways, right? You could say, well, look, this is the function of height 1, right? The function of height 1 over ab. Well, the area is just going to be 1 times this length, which is b minus a, right? The area here is b minus a. Or if if you're crazy, you break out the fundamental theorem of calculus and you say, well, I'm going to find the antiderivative and evaluate that thing between a and b, and so I get b minus a, right? But that's overkill, right? You just pulled out this huge machine to deal with this this tiny problem, right? So don't do that. And you can if you want, but it's overkill. Okay. Property number 3. The integral from a to b of some function plus the integral from b to c of that same function is what? You're integrating, you've got this function, you've got 3 points, a, b, c. You look at the integral of this plus the integral of that is going to be, Galen, go ahead, anybody? The integral from b to c of that function, right? And that's sort of obvious. Yeah, Isaac?
Reading integrals, they work from, you start with the bottom one and then you go to the top.
Yeah, so this is considered like the starting point and then the end point. Yeah. But that sort of brings up a convention. If somebody says, when they say the integral from b to a of a function, what they mean is negative the integral from a to b of that function. Okay, so if you go from this end and go the opposite direction, you take that to mean negative the integral in the positive direction. The fourth property has 2 parts to it and is probably the most important of these. So the first part is this, that the integral of f plus g, the definite integral of a sum is going to be, what do you think? You have 2 functions, you add them together, and you take their integral. Isaac?
The integral from a to b of f plus the integral of a to b of g.
Right. So it's going to be the integral of the sum is going to be the sum of the integrals. Oops. And then the second one is that if you multiply the function and then integrate it, multiply the function by some constant and then integrate it, well, then you end up with, as you might guess, the constant times the integral. Right? So this is, again, some sort of commutative statement, right? You're allowed to do it in different orders. You can add the functions first and then integrate them, or you integrate them first and then add them. Here you multiply the function by number and then integrate it, or you integrate the function and then multiply after. Right? And what we're saying is that it doesn't matter. And so all of these properties you can prove by looking at the definition. Okay. And so the book has a bunch of sort of, I think, what should be considered contrived and sort of silly problems. Let me show you maybe a couple of them. So here's one. They say the integral from 2 to 12 of f is negative 6. The integral from 2 to 6 of f is negative 12. What is the integral from 6 to 12 of f?
Does that say negative 6?
Yeah, negative 6. Okay, so take 30 seconds and do this problem, please.
Is that derivative?
Sorry? Negative 12, yeah. Okay, turn to somebody nearby and say, here's how I did it.
So this is just going to be like
Okay, so what do you get? Who wants to tell me the answer? Raise your hand if you want to tell me the answer. No, choose. Maybe I'll choose somebody who's not raising their hand. No, Isaac, what do you think?
Do you subtract them?
What?
If you subtract them, then you'll take out the interval from 2 to 6, and you'll be left with 6 to 12.
Is that right?
I don't know.
Yeah, sure it's right. Sure it's right. Because, right, this guy here is the integral from 2 to 6 plus the integral from 6 to 12. Right? This is the integral from 2 to 6 plus the integral from 6 to 12. If you subtract off the integral from 2 to 6, well, you're going to be left with the integral from 6 to 12. Right? Right, or more pictorially, right, you say, well, look, I know that the integral from here to here, oops, I know that the integral from here to here is kind of negative, right? Right, you know the integral from 2 to 12, and you know the integral from 2 to 6, right? So just take the integral from 2 to 12, take the integral from 2 to 12, and subtract off the integral from 2 to 6, and you're left with the integral from 6 to 12. Right? So you end up with whatever, right? 6. Everyone all right with that? Okay. Maybe a slightly more interesting one. The integral from a to b of f minus 3g is 3, and the integral from a to b of negative 6g plus 9f is 6. And they say, what are the integral of f and the integral of g? Okay, so again, take a minute or two and see if you can answer it. Okay, even if you haven't gotten it, turn to somebody and say, Here's how to do it. Okay. Somebody tell me how to do it. Arena.
So for f minus 3g, you
Yeah.
make you get f by itself, so
Okay.
you subtract 3g from both sides. So it'd be f equals 3 plus 3g,
Say the integral. at
or
some
the
point.
integral of f
Okay, the integral of f.
equals 3 plus 3g, or 3g.
Oh, I'm sorry. So this is the integral. I'm sorry. Maybe it's not. right.
Oh,
This is the
never mind.
integral of that whole thing.
I was looking at it weirdly.
Okay. 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 Anybody? Isaac. Yeah.
Can you distribute the integral over f over 3g and then move it?
Yeah, sure. Right. You can say, well, look, you've got this. You've got the integral of. You've got this integral. So let's. Right. The integral of a sum is the sum of the integrals, right? And you can pull the constant out. Oops. Right. Right. So yeah, you can. This is linearity, right? This is how you use linearity, right? The integral of the sum is the sum of the integrals, and the integral of a constant times a function is that constant times the integral of the function. Okay, so you can pull that out. Win.
I just use the elimination method for finding like a variable.
Mhm.
So I times the first one by -2, which would give you -2 integral of f minus or plus 6 integral of g, which you eliminate integral of g, which leaves 7f equals 0. So
Right,
integral
right.
of f equals 0 and
Right.
integral of g equals -1.
Right. So this basically boils down to a junior high school problem, right? Because here, so you get this first thing, and you get the second thing, which is the same thing as saying that the integral of nine integrals of f minus 6 integrals of g equals 6. Right. So using linearity, you reduce this to the following problem: x minus 3y equals 3, 9x minus 6y equals 6. Right. Right. Where your x is, here's x, and here's y. Right. You're trying to solve. If you're trying to solve for these unknowns, you can figure it out using junior high school math. So the point of this problem is basically that you can use linearity to make this into this. Isaac, yeah.
What did you do to get the coefficients? It was like the 9, the 6, and the 6.
So remember that linearity says that you're allowed to pull the coefficient through the integral, right? So if I have the integral of some number times alpha, some number times x, then that's just that number times the integral. Okay. So here I have the integral of f, the integral of minus 3g. Well, that's the integral of minus 3g is the same thing as minus 3 integrals of g. And so on and so forth. Everyone all right? Okay. Anyway, so the main thing is to know that you're allowed to do these. You're allowed to do these things. Okay. So there's a few other observations about the integral. which stated as theorems. First one, if f is integrable on AB, and f is always greater than or equal to 0, then it's sort of an obvious statement, right? If your function is always non-negative, then what are you going to say? Then the integral is also non-negative. Right. Certainly.
What does that word say after about?
Definite.
Okay.
Second one, also pretty straightforward. If f and g are integrable on AB, and f is always bigger than g, then what?
The integral of f is always going to be bigger.
Right. The integral of f is always bigger than the integral of g. Okay, the last one is maybe the most important one. If f and the absolute value of f are integrable on AB, then what? Can anyone guess what I'm going to write right here? What am I going to say about the integral of f and the integral of the absolute value of f? Isaac? No, right? You
No.
yeah, you weren't raising your hand. Everybody's looking at you. Maybe I should say it's a consequence of number 2. Win, go ahead.
Would the integral of the absolute value always be greater than or equal to?
Yeah, sure. Why? Well, because the absolute value function is always bigger than the actual function, right? It's also bigger than negative of the function, right? The absolute value of a number is always bigger than or equal to the number or the negative of that number, right? So what we see is that the absolute value, the integral of the absolute value is bigger than the integral of f. It's also bigger than the integral of negative f. Right? It's also bigger than the integral of negative f. I can abbreviate this, right, by just saying it's bigger than the absolute value of the integral. Yeah, Isaac.
Is there ever a situation in which the absolute value screws with our ability to do the integral?
So you're saying, like, suppose you have a function and it's integrable to start off with, but when you take its absolute value, it becomes non-integrable, right?
I think not.
I don't think that's going to happen, actually. Yeah, I can't think of an example. That's not going to happen, actually. Yeah.
Okay, that's 1, and then 2.
Yeah.
So I can always slide the integral into and out of the absolute value?
Nope. So it will change. It will change, right? Because you could have had, maybe your function looked like this to begin with, right? And so certainly in this case, the integral of the absolute value is not at all the integral of the function itself, right? But what this is saying is that the integral of the absolute value is always bigger than or equal to the integral of the function. In fact, it's bigger than equal to the absolute value of the integral of the function. Okay. This is actually another version of the triangle inequality. Remember the triangle inequality? Which said that, you know, if you take a sum of the absolute value of a sum, well, that's smaller than the sum of the absolute values, right? So that's basically the same thing that we're saying here, right? That the absolute value of a sum is smaller than or equal to the sum of the absolute values. Okay. This is like the discrete version of this statement. Right, because the triangle inequality, right, what that's saying is that if I have a bunch of areas, x1, x2, right, some of them are positive and some of them are negative, right? If I have a bunch of areas and I take the absolute value of the area, that's smaller than if I flip them all upwards and then I add them together, right? And that's basically what we're saying here with this picture, right? If I take the area under this curve and I take the absolute value of that, then that's smaller than if I flipped all these guys upwards and added them together. Okay, so it's exactly the same statement. It's just that one involves rectangles and the other involves curves. Yeah.
Why do you have two f's? What's the lowercase f?
Where?
There.
This f?
Yeah.
If f and the absolute value of f.
Oh, it's the same one.
Yeah, that's the same f. If f and the absolute value, maybe I don't even need to say this, but let's just say it, just to be safe. If f and the absolute value of f are integral. Okay. Let me just put up one problem. So the book gives this sort of problem. It says something like this. Find two numbers, a and b, that bound the integral from 0 to 1 of 1 plus 8x to the 5th dx. Okay, so what they mean is find a number that's bigger than this and find a number that's smaller than this. Okay, because can you integrate this at this point? In fact, can you integrate this at all? No, you can't. You can't get an antiderivative of this. Okay. But even though you can't get an antiderivative, even though you can't figure out what the integral is, maybe you can find some numbers, that tell you roughly the size of it. Okay, and so that's the point of this sort of problem. Okay. And so here's how, because there's only a minute left, let me show you how you do this. You'd say, if you look at this thing, on the interval 0, 1, right? What's the maximum value? What's the maximum value of this, and what's the minimum value of this? What's the minimum value? Say 1. Right? You know that this is, this is an increasing function, right? So the minimum is going to occur at 0. When x is 0, the function's value is 1. And what about on the other end? 3, right? Because on the other end, you've got 1 plus 8, the root of 9, that's 3. Okay. So what that's telling you is that here is 0, 1, here's 1, and here's 3. Okay, 1, 2, 3. Right? The function, the function rises like this, and we don't really know much about the function, but at least we know that the function is trapped between these two lines, right? Okay. So then you say, okay, well then the integral of this guy is going to be bigger than the integral of 1 and smaller than the integral of 3. Oops. Smaller than the integral of 3, right? And so you know that this integral, whatever it is, right, is trapped between 1 and 3. So you don't know the value, but you have some estimate of the size of it. Okay, and so that's sort of one way you can think about what's good about these observations, right? They allow you to say to get a rough estimate of the size of the integral, even if you don't know the integral. Okay, that's it for today.